All right, so now we're going to take a look at kind of the beginning of some applications that we're going to be interested in. We've been talking about this all along, so we're going back to this idea of the derivative that we're now getting these shortcut rules for is giving us the slope of the tangent line at a point, also known as the instantaneous rate of change, okay? So we're going to be able to work problems where they may ask us to find the slope of the tangent line, they may ask us to find the instantaneous rate of change, but what's nice about this now that we've had this section, it's going to basically be the idea that we are going to be able to do this using the shortcut rules. That we will be able to focus on the application, the answering the question, as opposed to actually doing the limit and the long way of calculating the derivative. All right? So one of the big applications that we're going to be looking at that we do quite a bit of work with is this idea of motion. We want to know where objects are moving through time, where they are, what their position is, as well as how fast they're moving at that given time. And then a little bit later down the road, we'll start talking about acceleration. But so the big application is motion. We're going to have a position function. In general, we call it S of t, but it might be x of t or f of t. It could be pretty much any type of variable we want there, but s is usually the common one that they use for the position function. And this position function could be something where it's giving the height of a ball at a certain time. It could be a position function where it's giving the position of a particle that's moving on a horizontal line. It could be all sorts of things that you're looking at. And then we want to talk about the velocity function. The velocity function is going to be a function that will tell you how fast the instantaneous velocity of the function at any given time. So of course we know that this has something to do with calculus. So the first idea, and this is our pre-calculus part, is that what we're going to do is we're going to calculate the average rates of change. So in pre-calculus, the average rate of change is nothing more than the slope of the secant line. The slope of the secant line requires 2 points in order to calculate it. So we have our point, A, S of A, which is giving us the time and the position. And then we have our point B, S of B, which gives us our second point. And then we simply want to calculate our slope. Our change in distance, change in position over change in time. That is going to give us our average velocity. So we're simply doing y2 minus y1 over x2 minus x1, slope of our secant line. The instantaneous rate of change, that's where our calculus comes into play. And calculus is where we're doing the limiting process. We are going to take these average velocities. We are going to take these slopes of the secant lines, and we're going to take the limit as h goes to 0, and we're going to find the limit of the secant line slopes. So we're going to do the limit of s of b minus s of a all over b minus a. And you might, and just remember that b minus a, that happens to be h, right? Because that's the distance, how far apart they were. And b would be your t plus h, and then your t. This is nothing more than your derivative. That's exactly what we are talking about in this problem. So instantaneous velocity, or this velocity function, is nothing more than the derivative of the position function. Now what you really want to do is kind of pay attention to what they're asking you for when they have problems in this, because you will need to know whether I'm using the position function, whether I'm using the derivative of the position function for velocity, and kind of working with that. So for example, let's look at our calculus textbook. We're going to drop it from a height of 100 feet. They're giving you the position, its height, in feet at any time in seconds, and here's my function, okay? And then they're going to have you find the following. Let's talk about this function. It should not surprise us that s of 0, if I were to plug in 0, I would get 100. This is my initial position. When time started recording, it was 100 feet tall. Look, right there is where that information is telling us. We're dropping it from a height of 100 feet, so at time 0, when I let it go, I had 100 feet high. Now, if I were to calculate, say, for example, S of 1, since I know I'm going to need that based on my interval down here, S of 1 is going to be negative 16 plus 100, or 84. That tells me that the book was 84 feet high at 1 second. So in that first second, it fell a distance of it fell 16 feet, okay? It started at 100, and then 1 second later, it had fallen to 84 feet. If I wanted to, I could calculate S of 2. I'll go ahead and do that right here while I'm at it. If I were to plug in 2, I get 4 times 16, which is negative 64, so we end up with 36. So the book was 36 feet high at 2 seconds. Okay, so the idea is that the function is giving us where the position of the book at any given time. Now, what they're asking me for in this problem, though, is they're asking me for the average velocity. So as soon as I see average velocity, I'm thinking slope of the secant line. To calculate the slope of the secant line, I need 2 points. I have the first point, 1, and then our S of 1, which we calculated over here, which was 84. And I have my 2, and then I calculate my position at 2, which was 36. So I'm basically using those 2 points to calculate the slope of the secant line. Our difference quotient, and in AP Calculus, you must always show your difference quotient, how you're calculating. We're simply going to go our average velocity from 1 to 2, so these are our times, is going to equal our S of 2 minus S of 1 all over 2 minus 1, which we'll go ahead and put our numbers in. We have 36 minus our 84 all over 1, which gives me negative 42. And I put my calculator in before I started this, and I should not have. 36 minus 84, negative 48. Can't add. And we like to include units. This would be feet per second, because I took the difference in position, the difference in feet, over the difference in time, feet per second. Units are important. It's almost always worth at least a point in a free response question. Now, you don't always have to show the points that you're using. As long as you show the difference quotient, you're showing what you're looking for. So our average velocity here is going to be S of 1.5 minus S of 1 all over 1.5 minus 1. So then we go get our values. We pick up our calculator to calculate each of these. S of 1.5 is going to be 64 minus my 84 all over 0.1. 64 minus 84 divided by 0.1. Hold on, I don't think I calculated that right. Let me double check my numbers. 1.5 squared times negative 16 plus 100 is 64. Oh, because it's not 0.1. I was like, no wonder the question of, I always make that arithmetic error for you guys. 0.5. So we end up with negative 40 feet per second for that one. Here, hopefully it goes smoother now. For C, my average velocity, S of 1.1 minus S of 1 over 1.1 minus 1. My S of 1.1, 80.64, minus my S of 1, 84 all over 0.1. I get negative 33.6 feet per second. I'm going to move this one down here because I ran out of room. Then we would do our average velocity for this last one. S of 1.01 minus S of 1 all over 1 minus 1.01 minus 1. So we're going to end up with that one. .6784 minus 84 all over 0.01. We get negative 32.16. Now notice that I didn't just pick these for no reason. Notice that as you're looking at these, I did 1 to 2, then I did 1 to 1.5, 1 to 1.1, 1 to 1.01. Oh, wait a minute. I'm picking the second point closer and closer and closer to 1. I am creating a limiting process where if I wanted to, and I was just happy with a guess, I could guess the answer to number 2. The instantaneous velocity, your slope of the tangent line, I could guess by looking at the slopes of the secant line as they are picking values that are closer and closer to 1. So I was negative 48, and then we were at negative 40, then negative 33.6, then negative 32.16. You can sort of see you seem to be heading toward negative 32-ish. Okay, of course we're not going to leave it at that. We're going to, instead of doing the limiting process, we now have these shortcuts. So I can guess, I get an idea of what it is, but this instantaneous velocity, I'm basically asking for v of 1. To find the velocity, I know that really what I need to do is take the derivative of the position function at 1. That's what they are asking me to find. So what I basically need to do, and I'm going to use my shortcut rules, is I'm going to find the derivative. Finding the velocity function is the same as finding the derivative of the position function. So I use my shortcut rules and get negative 32t. So this is what we're going to use in order to calculate the instantaneous velocity. So I basically then come up here and go, I would have negative 32 times 1, or negative 32. So I don't have to do the long limit definition. I don't have to do the difference quotient with the limiting process. I can use the shortcut in order to calculate this. I want to always put my units, and then just because we're going to start practicing our interpretation of this, what did we just find? What we found is that at t equal to 1 second, the book was, and because this is a negative velocity, we know that we were falling at 32 feet per second. Notice that this justification, and this is going to be something that's very important, it always has the instant. You always refer to what instant that you're doing. If I was doing average, I would refer to what interval, the instant. Then I am talking about the what. What was the thing that was moving? Was it falling or going up? What direction? What direction? How much? How fast? And always include units. You must have all 5 of these components in your explanation or your interpretation. What instant? What direction was it going? How fast? And what were your units? If you have all of that, you will get full credit and a free response for this. All right, so now let's come down here to number 3. And in number 3, now let's look at this question. We want to know how fast, so we're looking for a velocity of v of t. When the book is, how fast is the book traveling when it hits the ground? So the first question that you have, this is really a 2-part question. I first have to figure out when it hits the ground, number 1, and then after I find that, I will come over here and calculate the velocity at that time. So I will use the derivative. So I have 2 parts to this. Now let's think about it. When it hits the ground, it hits the ground, let's think about our position function. That's a position question. When your position is 0 feet above ground. So you have to recognize what formula you're using. So I'm looking for the position function. I need the position to be 0 feet above ground. So I'm trying to solve the equation s of t equal to 0, negative 16t squared plus 100 equal to 0. We solve that, t squared equals 100 over 16. And while yes, technically you would have a plus or a minus, you don't have a plus or a minus because we dropped the book. Time 0 is when this problem started, so we're only concerned about the positive value in this. So at 10/4 or 2.5 seconds, that is when the book hits the ground. The book, if I was interpreting, hits the ground at t equal to 2.5 seconds. There's my interpretation. But I'm not done with the question because the question was really, hey, how fast was it going? Okay. So how fast, when it hits the ground, in that I'm looking for the velocity. So I'm looking for the velocity with, at this time, 2.5 seconds. That's why this is a two-part question. So, and to find the velocity at 2.5, I know the velocity at 2.5 is using the derivative of the position function at 2.5, which we found above to be negative 32t, so negative 32 times 2.5, which is going to give me negative 80 feet per second. And again, that's because that's the velocity. If I was going to interpret this, again, just because we need to start practicing, we would say that the instant when the book hit the ground, you could, if you want to, say at t equal to 2.5 seconds, what the book was, what direction was it going in, falling at how fast, 80 feet per second. How much? In your units. That is your interpretation. So you want to get into the practice of when you are working these problems, not only should you do the math, you should also write the interpretation, because they're kind of picky about this on the AP, that if you do not give the correct interpretation, you will not get credit. It will not matter that you have a number written on your paper of 2.5 seconds. If you do not answer the question that they ask you and interpret it correctly and have all the components, the instant, what, which direction, how much or how fast, and units, you will not get credit for it. So I'm just going to start training yourself now. You got to do the math, but you have to answer the question.